how a 5,000-liter roof tank feeds 7 apartments through a booster set, header, and distribution lines. Over the course of this presentation, I'll walk you through the system's design, its components, and how it ensures reliable water pressure for all residents. So, let's get started and explore how this system works to keep everyone comfortably supplied with water. Let's take a closer look at the design brief for this project. We are working with a 5,000-liter rooftop tank, which uses a submerged pump to supply water. The primary service points include 7 kitchens and 21 bathrooms, so it's a fairly large and complex system. A key requirement here is maintaining a pressure of 1.5 bar at the header. This is crucial to ensure that water flows efficiently and consistently across all these outlets. Overall, this brief sets the foundation for our design approach, focusing on capacity, service needs, and pressure requirements, all of which are vital to delivering a reliable water supply for the entire facility. Let's take a closer look at hydraulics in this system. The flow rate is typically around 5 to 6 cubic meters per hour, which is a solid, steady flow for efficient operation. Thanks to the 2-inch header, the pressure losses are kept quite low, less than or equal to half a bar, helping to maintain consistent pressure throughout the system. One of the key points here is velocity, keeping it at or below 2 meters per second. Why does that matter? Well, lower velocities contribute to quieter operation and help reduce water hammer, which can cause noise and even damage over time. Overall, these hydraulic parameters are designed to optimize performance, ensuring the system runs smoothly, quietly, and reliably as part of our larger goal to improve efficiency and longevity. Let's talk about pump selection and pressure tanks. When choosing a booster set, it's common to have a duty and standby pump configuration. This setup ensures reliability and continuous operation, especially during maintenance or if one pump needs servicing. We aim for a constant pressure of around 1.5 bar, which helps maintain consistent water flow throughout the system. Now, regarding the pressure tank, a capacity of 150 to 200 liters is typically suitable for many applications. The type of tank used is usually a diaphragm or bladder tank, which effectively isolates the water from the air cushion. This design helps maintain steady pressure and reduces pump cycling, ultimately extending the lifespan of your equipment. Connecting these points, selecting the right pump and tank ensures your system operates smoothly, efficiently, and reliably, aligning with the overall goal of a well-designed water supply system. Let's take a closer look at the piping and valves setup here. On the suction side, we have an isolation valve paired with a waste strainer. This combination is crucial because the isolation valve allows us to shut off the flow for maintenance, while the waste strainer helps filter out debris to protect the system. Moving to the discharge side, we've got a non-return valve, or NRV, along with another isolation valve and a pressure gauge. The NRV ensures flow only moves in one direction, preventing backflow and safeguarding system integrity. The header itself is 2 inches in diameter and is equipped with an air vent to release trapped air, which is vital for maintaining efficient operation. From this header, there are 3 branches, each 1 inch in diameter, allowing us to distribute flow effectively to different parts of the system. Connecting all these components thoughtfully ensures reliable operation and ease of maintenance, which ties directly into our overall focus on system efficiency and safety. Let's take a look at the electrical and controls section. Here, the system can operate in different modes depending on the application. For example, it can run in a constant pressure mode at 1.5 bar when using the VSD, or in an on-off mode within the range of 1.2 to 1.5 bar. This flexibility helps optimize performance based on demand. The control panel is equipped with essential safety and control features. It includes a miniature circuit breaker, or MCB, to protect against overloads and short circuits. There's also an overload protection device, or OL, to prevent damage from excessive current. Additionally, the panel features alternation, which ensures even wear and tear by switching the operational cycle between components. There's also a dry run interlock, which is a critical safety feature that prevents the system from running without water or proper conditions, avoiding damage or malfunction. Overall, these electrical and control features work together to ensure reliable, safe, and efficient operation of the system, aligning with our goal of optimizing performance and safeguarding equipment. Now, let's talk about our operation and maintenance routines. On a weekly basis, it's important to clean the strainer to prevent any buildup that could hinder performance. We also need to check for leaks and any unusual noises, as these can be early indicators of potential issues. Moving to the monthly tasks, we log the pressure readings and monitor pump cycling. This helps us spot trends or irregularities over time, ensuring everything stays within optimal ranges. Additionally, having the right spares on hand is crucial. I recommend keeping seals, NRV kits, and gaskets readily available. This way, if a part needs replacement, we can act quickly and minimize downtime. These routine checks and stock preparedness are key to maintaining smooth, reliable operation and aligning with our overall goal of efficient system management. Let's walk through the key components of the PFD. Starting from the roof tank, the fluid flows downward to the booster pumps, which are essential for maintaining the required pressure and flow rate. From there, it moves through the NRV, or non-return valve, to prevent backflow and a gauge to monitor the pressure levels. Next, it passes through a reducer, going from 1 inch to 2 inches in diameter, which helps manage flow rates efficiently. After that, the flow continues through a 2-inch header, serving as a main distribution point. Finally, this header branches out into 3 1-inch lines, which distribute the fluid to different parts of the system. This setup highlights the importance of controlling flow and pressure at each stage, ensuring the system operates safely and efficiently. Connecting these points back to our overall theme, you can see how each component plays a vital role in maintaining a reliable and well-regulated system. Now let's take a closer look at the P and ID, or piping and instrumentation diagram, which is crucial for understanding the system layout. Here, you'll see the instrumentation and tagging details. For example, the T201 is the roof tank, and the PU201 refers to the pumps. The VPTK201 is the pressure tank, which plays a vital role in maintaining system pressure. You'll also notice the XV101, which is a valve, and the PiPT201, representing pressure and temperature instruments. Lastly, the HD200 is the header that connects various components. These tags and instruments are essential for monitoring and controlling the process effectively. They help us visualize how each piece fits into the overall system, ensuring safe and efficient operation. Remember, understanding these details is key to troubleshooting and optimizing the process, which ties back to our overall theme of system reliability and control. Let's take a closer look at the Bill of Quantities, or BOQ, which outlines all the key components needed for this project. Starting with the booster pumps, we have 2 units designated for duty and standby, ensuring reliability and continuous operation. Next, there's a pressure tank with a capacity between 150 and 200 liters, which helps maintain consistent pressure in the system. Moving on, the roof tank is significantly larger at 5,000 liters, serving as the main water storage. For controlling the flow and isolating sections of the system, we have 10 1-inch isolation valves, which are crucial for maintenance and safety. We also include a Y strainer, again 1 inch, which filters debris from the water to protect downstream equipment. To prevent backflow and ensure proper flow direction, there are 2 non-return valves, or NRVs, also 1 inch. Monitoring system pressure is vital, so we've included 2 sets of pressure gauges with transducers, providing real-time data for system management. The header pipe, which is 2 inches in diameter, along with its fittings, forms the main conduit for water distribution, and there's a similar setup for branch pipes, 1 inch in diameter, also with fittings. These distribute water to different zones. Finally, there's an electrical panel equipped with MCBs, overload protection, and VSDs, which control and protect the pumps and other electrical components. All these elements together form the backbone of the water supply system, and understanding their roles helps us appreciate how each part contributes to a reliable, efficient operation.